Chapter 1, Section 4 is on parametric functions. What we need to understand about parametric functions is that unlike a typical function in which y is described in terms of x, we now can describe both the x-coordinate and the y-coordinate in terms of another variable, and that variable is going to be time. We're always going to have a time element with parametric functions. So instead of having something like y equals x squared, where the value of y is dependent upon whatever you put in for x, now x and y can both change according to time. And this is really nice to be able to have this because there are many real world situations that change over time, and we want to be able to graph both the x and the y coordinate with respect to a time element. So parametric mode is very helpful, particularly when we're trying to graph things that are not a standard function, such as ellipses, hyperbolas, sideways parabolas, curves that are not functions that can be written y in terms of x. So we're going to look at a lot of those situations. But just to investigate, we're going to start with this first example. Much of this assignment is going to be done using the graphing calculator. So please make sure you have it out. Come back and look, because I'm going to be doing this using the TI Smart View. So a lot of what we're going to be doing is taking a look at the TI Smart View and how to plug it in. So here, in this situation, x is described as the square root of t, y is described as t when t is greater than or equal to 0. So here's the parametric mode that we need to type in. But there are some unique situations with parametric mode that we will take a look at in the calculator. So call it, get your calculator out, get it ready, and I'll call it up right here. Okay, I'm going to call up the TI Smart View. Here it is. This will allow you to see the keystrokes as I go along. Sometimes this will be better than what we'll be using in class. So please, if you can follow along, that's great. Because the very first thing that we have to do once our calculator is on is we have to change the mode of our calculator. If you go into mode, we can see there's normal scientific engineering mode. We can change the float, radian to degree mode. Please make sure your calculator's in radian mode all year long in here. We will never use degree mode. And then it says function, parametric, polar, and sequential. You'll use sequential some in AP statistics, but not much in here. Okay, what we want is parametric mode. So we come over to here and we hit enter. And we are now going to be in parametric mode. This makes a big difference when we are in parametric mode. Notice over here in this area, right here, okay, we are getting the keystrokes that I'm actually punching. So you should be able to take it keystroke by coming back and looking at this if you would like. Okay, so I'm going to go to y equals now. And notice when we go to y equals, all of a sudden we get this change here. We get this situation where the x-coordinate and the y-coordinate is being described. And the x-coordinate was going to be, if we need to take a look, we'll go back and look at this here real quick. Okay, the x-coordinate is the square root of t, and the y-coordinate is just t. So if we come here, the x-coordinate, we're going to go second x squared to get the square root. And notice, if you look at this, the button, the xt theta n, if you are in function mode, it'll be an x. If you're in parametric mode, it'll be a t. So all you have to do is hit this button right here, and you'll automatically get a t. And we'll hit enter. Now we got to describe the y-coordinate. And the y-coordinate said it was just going to be t. Now, the interesting part about parametric functions, it's not enough just to define the x and the y coordinate. We also need to be able to set the parameter interval, is what you're going to find out that it's called. And what does that mean when we set up a parameter interval? Well, we need to change the window. So we need to look at, on our calculator, where the window button is on the graphing calculator. So if you look in the top row, it is the second key here. And if we look at the window, it changes as well. It gives us x minimum, this x maximum, in a t step. What is this t step business? And then we still have this x min, x min, x max, and x scale, y min, y max, y scale. Well, here's the whole idea about it. Now that we've introduced this additional variable time, we need to make sure that it only graphs it over the time that we want it. And it was described back in the problem. If you look back at this problem right here, it says it only wants it when t is greater than or equal to 0. So when we are in our calculator, that means that the smallest y value, the smallest time, should be 0. So I'm going to hit enter. And then my t max, it has to be something that takes me off the screen. If I leave it too small, it will be a problem. So I'm going to maybe make it 10. We'll see if that's enough to take it off. Okay. The t step here is very, very important. If we make the t step too small, I won't see a good detailed graph. If I make it too small, it'll be too detailed. If I make it too large, I won't see enough points. So I'm going to leave this at 0.1. 0.1 is typically a good scale for our t-step. You can leave what was in there is fine. The x-min and the x-max looks fine for now. And if we graph this thing, if I go ahead and hit graph now, okay, here's what we get. Here's a picture of this. It's only graphed right here on this. It didn't graph over on the right-hand side, but it looks like it's half of the parabola x squared. And that is essentially what it is. Watch what happens if I go back to my window here and I change this to go from 0 to 1 only. I change this to a 1. And now if I graph this thing, it stops. It doesn't go off the screen because it's only graphing this from time equals 0 to time equals 1 every 0.1. That's not good. That's a problem. You have to make sure that your time element will take you off the screen. In this case, it's 10. And you just got to play around with it sometimes to see exactly what your time interval should be. Okay, so I'm going to go back to a 10. Likewise, watch what happens if I make my t-step only every 1 instead of every 0.1. It's not going to look the same. If I graph this, it looks all choppy. As a matter of fact, if I change this to be, let's say, the t-step to be 2, watch what happens here. If I make it 3, it's even really worse. Okay? And graph this, it looks like it doesn't look like a parabola at all. And the problem is that what's happening is it's looking at when time equals 0 and it's plotting the point 0, 0. Then the next time that it's looking at is 3 time units later. It's way out here off the screen and it's only connecting those 2 dots. So what you need to know about the t-step, it's the time interval. Okay, so when we set this, and if I'm going to go from 0 to 10, I need to get more detail. So essentially, the way to read this is I'm going to graph this from time equals 0 to time equals 10. You want to think seconds, think seconds. It's a time element. It's not a second. It might be a tenth of a second or a hundredth of a second, but it's some time interval that's 10 units long. And we're going to graph it every 0.1 of those time units. So it's going to graph between 0 and 10. It's going to graph 10 different points between 0 and 1, 10 different points between 1 and 2, and so on. So we're getting a detailed picture of what's happening. To be safe, a good t-step is generally 0.1 for most of what we're going to be looking at in this class. So if we go back to this picture, here's what we get. So you need to know how to type them in. Now let's go back and confirm algebraically to see, is this really half of a parabola? So if we come back, it's already typed up for you because I had it typed up in the notes. And it simply says, if we want to verify algebraically, it's pretty easy. You just have to solve for y in terms of x. Right now, y is equal to t. If I want to replace t in terms of x, I've got to look at this equation right here that says x is the square root of t. If I square both sides, x squared equals t. And that's how we get y equals x squared. It is the parabola y equals x squared. The problem is it's only the right-hand side of that. The reason it's only the right-hand side is because if t is only greater than or equal to 0, then we're only looking when x is greater than or equal to 0. So yes, it is the function y equals x squared, but we also have to limit the domain. So think about this. In our graphing calculator, it's really nice. In order for us to have one-to-one functions, okay, that can only happen if the function's always increasing or always decreasing. And y equals x squared, that's not the case. But if we limit it to be y equals x squared, comma, when x is greater than or equal to 0, now that has a one-to-one portion to it. So, but how could we do it on our graphing calculator? How could we graph only the right-hand side of a function and leave the rest of it off? Difficult to do. But now with parametrics, it becomes easy to do. Okay? So you always have to define the x-coordinate. You always have to define the y-coordinate. You can look at those keystrokes to see how we set that up. Let's look at the second one. Definition. Parametric curve or parametric equations are defined as follows. X and y are given as functions. X equals some function in terms of time, and y equals some function in terms of time. Over an interval of t values, then the set of points x comma y, which is just f of t comma g of t, defined by the equations, is called a parametric curve. The equations are parametric equation for the parametric curve. So the picture itself is called the parametric curve. The equations for x and y are called the parametric equations. So we know terminology. Next, this is very important. The variable t is called a parameter. That's how you read this. It's called a parameter. For the curve, and its domain I is called the parameter interval. If I, this parameter interval, is closed interval from A to B, the point f of a comma g of a is called the initial point of the curve, and the point f of b, g of b is called the terminal point of the curve. Don't make this more complicated than it is. You simply plug in the smallest time interval into the x-coordinate and the y-coordinate to get the initial point. Likewise, you simply plug in the largest time interval into the x-coordinate and the y-coordinate to get the terminal point. Okay, it won't be hard, it'll be very easy. But what is important is that a graphing calculator can draw a parametricized curve only over closed intervals. So the portion it draws always has to have endpoints, even when the curve being graphed really does not. Keep this in mind when we set up our graph. In other words, we always have to have a Tmax and a Tmin, even when sometimes we shouldn't have a Tmax or a Tmin. The graphing calculator requires us to put it in. So we need to make sure whatever we pick for a Tmax or a Tmin, it takes it off the graph, the viewable graph. Okay? Here's a nice exploration that we're going to run through a little bit here to see how this goes, just so you can see how some of this works out. We're going to start out with letting a equal 1, 2, or 3 and graph the parametric equations in a square viewing window using the parameter between 0 and 2 pi. How does a affect this graph? So let's take a look. First of all, we'll start with this coefficient here being 1, and then we'll change it to a 2 and then to a 3 and see what that does to the curve. So we're going to be doing quite a bit on the graphing calculator here. Here it is. It's cosine and then sine. So again, once we get into x equals, we go, the coefficient's 1, so that's fine. We're going to go sine of t, close that, and then we're going to go cosine of t, close that. Okay. Okay. There are our curves. Now when we set up the window, we have to be very careful here. If we set up the window, we need to make sure we're looking at the values. Again, if we come back here, this is going to be defined between 0 and 2 pi only. That is the parameter interval for this first part here that they're asking us to do. So we are going to go our window. We'll go from 0 to 2 pi. When we type it in, we're going to go 2. Our pi key is second right here, the up arrow key, and then hit enter. It's going to convert it to a decimal, but that's okay. It doesn't matter. Our t-step here, you can leave it 0.1. If you want to make it that 0.13, blah, 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 that it had, that's fine. For now, I'm going to leave it go from negative 4.7 to positive 4.7. I'll show you how to square that up here in just a minute. If we take a look at this graph, if we hit graph, here's what we get. Nice. It looks circular. Some may say maybe it's not quite a circle. If you're not sure, you can go zoom and go zoom square. So zoom 5. And now we definitely get a nice circle. We can square that up. So the bottom line is this is a picture of a circle, and you should put that in your notes so that you see that picture. If we go back to this problem, the second thing that it asks us to do is, okay, now make the coefficient here for A be a 2 and a 2, and then a 3 or a 3, okay? So let's go back and take a look at this, see what happens. So if I go back to my y equals, and I'm going to insert a 2. If I go second, delete, notice that the cursor now is blinking. That means I'm in insert mode, and I can put a 2 there. And I'll cursor down, and I'll do the same thing. Second, insert, and I'll put a 2 there, and I'll cursor down. And now I'm going to graph this. If I graph it, let's see what happens. It looks the exact same, except now it's a circle with a radius of 2 instead of a radius of 3. So it appears that this is just changing the size of the radius. Let's go back to y equals. And let's change this to a 3. And then cursor down, change it to a 3. Hit enter. Let's graph this. And sure enough, now we get a nice circle of 3. Notice, remember, before it was difficult to graph circles if we just wrote that in function form. So now it makes the process of writing these circles much, much easier. Okay? Let's go back to this problem. So essentially it says, how does this changing A affect this graph? It changes the value of the radius. Okay? All right, 2. Let A equal 2. We're doing the same thing, but now we're going to mess with the parametric equations by changing the parameter intervals from 0 to 2 pi, then 0 to pi, and we're looking at a bunch of different intervals. Describe the role of the length of the parameter interval. So we're just trying to play around to get a feel for this. So if we come back, if we go to y equals, we're going to make this a 2. It really doesn't matter if you left it a 3. They said just let's do it with a 2. That's fine. Okay. But the very first time we're going to set this window. Now we're going to go, if we come back and look again, the first interval that they wanted us to do. The very first interval was 0 to 2 pi, and then we're going to go 0 to pi. So we're going to start, this is 0 to 2 pi right here. If we graph it, we've really already done it. So you can provide that graph in your notes. But now let's just make it go from 0 to pi. So if I change my window, and now I'm only going to go from 0, enter, to pi. And we graph this. Look what happens. Now we only get half of a circle, the right half of the circle. We're not getting the left half, only the right half. And that's because we're starting at time 0 and we're ending at time pi now. So it makes a difference in the length of the curve, how much of the circle we actually graph. Let's see if that happens with the rest when we go back and check these other intervals. So we want to check 0 to 3 pi over 2. We want to check 2 pi to 4 pi. That's an interesting. And then we want to check 0 to 4 pi. Okay? So we're coming back to the graphing calculator, and we're going to check 0 to 3 pi over 2. So here's my window. I'm going to go 0, enter. Then I'm going to go 3 pi divided by, oops, divided by 2. Okay, I'll leave my parameter or my step the same. Let's graph this and see what happens here. Here it comes. Now we get 3/4 of a circle. It left off that last quarter. Here's the window again. What happens if we go from 2 pi to 4 pi? 2 pi to 4 pi. And hit graph. We get the complete circle. However, the time element really started with 2 pi instead of 4 pi. So what happens if we go from 0 to 4 pi? 0. This is still 4 pi. Watch what happens. It should go around twice. Here it comes. Notice it's still working, and it comes around again. So the nice part about parametric mode is you can graph more. It can be you can represent this particle traveling around in a circular fashion and really just going around and around if you want. Just to illustrate the importance of the t-step, watch what happens if we come back and we change this t-step. If I come down here and I change this to a 1, it's not going to look pretty. Watch what happens. That's not looking very circular. Again, it's only graphing a new point every 1 time element. 1 second if you want to think of it that way. So it's going to graph it at this time element is 0, but then the next one isn't until the time element's 1. It's going to connect those 2 dots. That's why it's important for our t-step to be small enough to give us a precise graph. Make it 0.1, graph. Here it is. All right. So what is changed if we come back and answer this question? Let A equal 2. What is changing here when we change the size of the parameter interval? It's changing the period of the function. And period maybe isn't the best word, but it's changing. It changes how much of this curve is going to get graphed. Okay? Changes the period of the curve. All right, for part 3, we're going to be similar, except A is going to equal 3 this time. So if we go back, A is going to equal 3. We're going to graph it over these 4 parameter intervals. Okay? And we're going to look at how does that change the initial point and the terminal point in each case. We can see it as it graphs. So here it is. We're going to go from pi over 2 to 3 pi over 2 the first time. Then we're going to go from pi to 2 pi the second time. Then we're going to go from 3 pi over 2 to 3 pi the third time. And then we're going to go from pi to 5 pi on the fourth one. Okay? So you can tell your initial and terminal points simply through the graph as well. It wants us to use A equals 3 on this one. It really doesn't matter. You can leave it as A equals 2 if you like. That just changes the size of the circle. But since it said to change it to 3, we'll come to Y equals. We'll change it to 3. We like to do what they tell us to do. Okay? And now when we set the window, the very first time we're going to start at pi over 2. And then we're going to go to 3 pi over 2. And we're going to graph it. Watch where it starts and watch where it ends. The starting point was the point 3, 0, and the ending point was the point -3, 0, as it graphed half of this circle. So write those down, the starting point and the terminal point. So if I was going to write that down back here under this first one, okay, the first situation, it would be initial point is going to be 3, 0. Terminal point is -3, 0. Okay? That's where the initial point's where it starts, the terminal point's where it ends. It's that descriptive. It's that simple. Okay? Let's go back, check the second interval. Now they want to change our window to pi and 2 pi. So here it is, second pi and 2 pi. Let's graph this. Let's see where it starts. Now it starts at 0, -3, and ends at 0, +3. So here it is. So the second one here, I'll circle it in red. The initial point is going to be 0, 3, 0, -3, and the terminal point is going to be 0, 3. Okay, for the red one. Let's kind of do each one. Okay, so it's changing where it starts and where it ends. Let's check the third and the fourth one just to see if it continues to change these starting and ending points. So the third one was 3 pi over 2 to 3 pi. So going back to our window, we have 3 pi divided by 2, and then we have 3 pi. We're going to 3 pi. If we graph this, here it is. It starts at -3, 0 and goes to 0, -3. So initial point on this one was -3, 0. Terminal point was 0, -3. Okay? That's this one. This is the blue interval. The last one I'll do in black. Here it is. Change the window. We're going from pi to 5 pi. And if we graph, here it is. It's kind of hard to tell where that one was starting and where it was ending. We'll do it again. Go to Y. Kind of see if we can graph this thing again. I just had to change it so it will graph over it. Okay. We hit graph. It's starting down here at 0, -3, and it's coming back to 0, -3, but it went around twice. That's the key. If you watch it carefully, it goes around twice. So in both these cases, on this last interval, it starts at 0, -3, and it ends at 0, -3. That's okay. That can happen. Okay? Last one. We're going to do something very similar. It says graph it now. We're going to go 2 cosine of -t and 2 sine of -t. It's given us these 3 intervals. In each case, describe how the graph is traced. So we're going from 0 to 2 pi. We're going from pi to 3 pi, and we're going from pi over 2 to 3 pi over 2. Okay? So let's take a look. Coming back to our calculator here. So again, y this time is going to equal 2 sine of, or it's actually cosine now. They change it around here, which is fine. This is cosine of negative. Don't forget to use this negative sign right there of t. You can see the buttons. They become red as I hit them. And then we're going to go enter. We're going to go to sine of negative t. Close it. Okay. Just going to go back and check to make sure that's what they wanted. Okay. Yes. 2 cosine of negative t, 2 sine of negative t. All right. Here's the smart. Back to this. We're going from 0 to 2 pi the first time. So here's our window. The t min is going to be 0. The t max is going to be 2 pi. And we're stepping point 1. If we graph this, here it is. It started at the point 20 and it came around to the point 20. Gave a complete circle. So you would list the initial point, the terminal point, and that it's a circle of radius 2 being graphed. Now let's do the same thing, but we're going to go from pi to 3 pi over 2. So we're going pi to 3 pi. Not over 2, just 3 pi. And watch what happens here when we graph this. Okay? Now it starts at negative 20 and comes around to negative 20. But in both cases, okay, it was going in the clockwise direction. Watch what happens on the next one. See if we get the same thing when we go to a window. We're going to pi over 2 to 3 pi over 2. Pi divided by 2. And then we have 3 pi divided by 2. If we graph this, okay, it still goes in the clockwise direction. It's half a circle starting at 0, negative 2, and going up to 0, positive 2. So you would give those initial points, those terminal points, graph it, describe what's going on. And you're going to see more now as we get into some of the examples. But that's a nice little exploration to take you through what the parameter interval does, what the t-step does, what happens if we change coefficients in front of that sine and cosine, and we're actually going to see the problem. Why is it a circle? How can we confirm it algebraically as we continue with this lesson? Okay, so there's the first page of that exploration. Let's keep going on to the next slide. Okay, let's take a look at some examples here. This says, for x equals a cosine of t and y equals a sine of t, we get the following situation. This is really, really important that you can do this. This is how we're going to confirm this. Okay? If we square, essentially, if we take this and square both sides, you get x squared equals a squared cosine squared of t. If you take the y equation and you square both sides, you get a squared sine squared of t. Okay? That's what it's going to look like. And the key is, what we know is that when we add sine squared and cosine squared, we get 1. That is a trig identity that we have to have memorized. So if we add x squared plus y squared together, we get a squared cosine squared of t plus a squared sine squared of t. And we can factor out an a squared out of both of those terms. When we do that, we get sine squared t plus cosine squared t. And sine squared t plus cosine squared t is 1. Therefore, x squared plus y squared equals a squared. And that's why the number out in front will always represent the radius, because x squared plus y squared is the standard form of a circle, where this a is the radius. Okay? That's why we always get a circle with the center at the origin. The key is when we're verifying, if we have sine and cosine, we want to square both sides of the equation and prove this algebraically. There are going to be problems in which we're going to be doing this exact same thing to prove, as well as with ellipses. Let's take a look at another example. In each of the following examples, first of all, a parametrization is given for the curve. We want to graph the curve. What are the initial and terminal points, if any, and indicate the direction in which the curve is traced. So the very first thing we're going to do is find the initial point. And then we're going to find the terminal point. And I think you should be able to do this without a graphing calculator. To find the initial point, plug 0 into the x-coordinate and plug 0 into the y-coordinate. If you plug 0 in, the initial point is going to be the cosine of pi. And if you plug 0 into the y-coordinate, you're going to get the sine of pi. Now, we don't want to leave it like this. We need to know what the values are. If you still do not know how to evaluate quadrantal angles, sine and cosine, of a unit circle, you need to get this unit circle memorized. A quadrantal angle, sine is represented by the y-coordinate, cosine is represented by the x-coordinate. So when I want to find the cosine at pi, here is pi. It's this right here, that angle. The cosine is the x-coordinate, which is -1. The sine at pi is the y-coordinate, which is 0. So this should be our initial point for this curve. We will see it in a minute when we put it in the graphing calculator and graph it. Likewise, if we plug in pi, which is the end point for this curve, if we plug pi in, pi minus pi is 0, you get the cosine of 0 for the x-coordinate. If you plug pi in here, pi minus pi is 0, you get the sine of 0. But again, we don't want to leave it written like this. What is the cosine of 0? The cosine of 0 is right there. It's the x-coordinate. It's 1. The sine at 0 is the y-coordinate at 0, which is 0. So our initial point should be -1, 0, and our terminal point should be 1, 0. And it's going to be, it looks like it's going to be circular, but who knows, maybe it's an ellipse. Let's take a look at it in the graphing calculator. It's pi minus t for the argument. So here we go. Y equals, okay, the sine of pi minus t. Let's make sure it was the sine. Okay, is going to be the cosine. Okay, so here it is. I'm going to clear this out. This is the cosine of pi subtract t. Okay, close it. I'm going to hit enter. I'm going to clear this out. I'm going to go sine of pi minus t. Sine of pi subtract t. Subtract t. I'm going to close it. Okay. Now we have to be very careful of our parameter interval again. If we come back and we look at this, it says it only wants this graph between 0 and pi. That's going to describe your parameter interval. So my window is going to go between 0 and pi. My t-step of 0.1 is fine. Zero and pi. And I'm going to graph. Here it is. It's the top half of a circle. The initial point did start at -1, 0, and it did end at 1, 0. So we'll come back. When it says it asks you to graph it, Okay? It wants to see a nice graph of what's going on here. So we simply have to make this point negative 1, 0, this point 1, 0. This is the point 0, 1, and we'll graph it. It starts here, and it comes around. It is half of a circle. It's hard to draw on these smart boards, but there it is. But it also wants to know a directed distance, which means it started at this point and it went this direction. So we just put a little arrow like that that indicates it's going in that direction. We will do that every time that we graph a parametric curve. Okay? There it is. What portion of the graph is curved? Gives everything right there. Initial point, terminal point, there's the curve. How do we verify this thing algebraically? Here's how it works. If it's sine squared and cosine squared, let me say that again. If it's sine and cosine, you always start by squaring both sides. So x squared is going to be cosine squared of pi minus t. Likewise, y squared is going to be sine squared of pi minus t. And it is sine squared of pi minus t plus cosine squared of pi minus t will equal y squared plus x squared. And we know that sine squared plus cosine squared, as long as it's the same angle, it equals 1. So 1 equals, it doesn't matter what order you add in, x squared plus y squared. There is the circle that it equals. It's the unit circle. But it's only defined. It's very important that you say this is only going to work when y is greater than or equal to 0. In other words, the y values are restricted here. It's only graphing when y is less than or equal to 1, greater than or equal to 0. That's the only portion of this curve that's being graphed. Okay? Another way to say the same thing is to actually solve for y by subtracting the x squared over and taking the square root. And typically we would go plus or minus 1 minus x squared. But we don't have to worry about the plus or minus now. We're only looking at the positive values for y. We don't have to worry about the negative. It's the same thing as saying this. So I don't care which direction you go, if you name it like this in blue or you name it this way and restrict the range. Either way is fine.